Sagar sir.
Yes, sir. Good evening.
Sir, good evening, sir. Sir, we can start, sir, today's session.
Okay, sir. Yes. Sir, can you confirm? If
Yes,
you're
sir.
able to see my screen?
Yes, sir.
Okay. Thank you, sir.
Full screen is not there, sir.
Yeah, I'll make it full screen.
Okay.
So let's have a brief overview of what we have discussed yesterday, and then we continue our session for today. So yesterday we started with the discussion of what AI is, how can we make computers or systems think and mimic the behavior of a human being, represent a human intelligence. For that, first the system should be able to learn. And how can we make a system to learn? We make a system to learn using the concept called as machine learning. So what is machine learning? Machine learning is a science where we help the machine by feeding some input data along with its output, and we ask the machine learning algorithm, we choose a machine learning algorithm that would try to figure out how an output can be generated given the input. So in a nutshell, that's what machine learning does. So today what we are going to do is we will understand what happens inside this yellow box with the help of a couple of examples. Okay. Once we are clear with this, like what happens in this yellow box, how we generate this function that can create this output from this input. So if we have that understanding, then we are good to go with artificial intelligence. So that becomes the building block for us to go ahead and start learning about artificial intelligence. So let's get started with understanding what happens inside that machine learning box. Though we just represented it as a box, there has to be something that's happening inside that area which we call as the learning process. Now let's understand that learning process. Okay, let's simplify the learning process. If we take a complex problem, it would be difficult for us to understand what happens in the learning process. So let's simplify it. For simplicity, the two learning process that we are going to see today, one is named as regression, the other one is named as classification. So these are the two types of learning that we are going to see today. So regression is when the output is a number like price. Example is price. Classification is when the output is discrete. We call them as classes. For example, here binary, which takes values like yes or no. So this is the major difference between the regression and the classification. When our output is numeric number, when we are predicting something like a price, then we go for regression. When our output is discrete, then we go for classification. Now let me explain regression problem for you. Then we will see a classification problem as well. Let's take only one input and one output. That's why I said simplicity is always good, right? So start with only one input and one output. My inputs are something like, let's say 5, 5.6, 5.8, 5.4, 5.2, and 6. My output Y is, let's say 58, 64, 69, 66, 70, 81. I randomly choose something. Don't pay attention to these values. Now this is my input. Okay, this is the input. This is my output. So we pass this input and output to this machine learning layer. So this is going to be X and this is going to be Y. What we expect as an output from this is an equation where we can find out the value of Y with the form of f of x. So this is what is expected, right, from the machine learning. Now let's see how this works out in practicality. First of all, let's see x and y in the form of a plot so that we will understand how it works out. X is ranging from 5 to 6, y is ranging from, let's say, 58 to almost 81. I'm not giving the complete scale. So here the scale is truncated. So let's point these things. So maybe it looks like this. This is how the data looks like, right? Now, what mathematical function can represent the relationship between these two data points? We need to think that. It's not magical that you give any input and you give any output. We can generate that output from the input. No, there has to be some basis. There has to be some relationship between the input and the output through which we can represent them in the form of a mathematical equation. So here, just let's assume that this can be represented with a linear line like this. I just draw an imaginary line there. Don't think that that is the line, but we want to represent the relationship between the input and the output with an imaginary line. That line is a linear line. And generally, how do we represent a linear line? So we represent a linear line like this. Y is equal to mx plus c, where m is called the slope and c is the y-intercept. So this is coming from the basic algebra. So long back in the school days, we have learned this. So a linear line will be represented in the form of y is equal to mx plus c. So let's assume that we can represent this line with this linear equation, y is equal to mx plus c. Now, we know the value of x, x is the input. We know the value of y, y is the output. What we don't know here is the value of m and the value of c. So we need to find out what value of m and what value of c, when substituted in this equation, will generate this output from this particular input. So that's the learning part. What we are trying to learn here in machine learning is we are trying to represent the relationship between input and output using a mathematical equation and find out the unknowns in that mathematical equation which defines this relationship. That's precisely what we call as the machine learning. Now, let's do this. Let's do this. What inputs we have? I have 58 is equal to m, which is not known for me. So I will keep it as it is, into 5. So x is 5 for the first observation, plus c. Second Second observation, 64 is equal to m into 5.6 plus c. Similarly, for the last observation, 81 is equal to m into 6 plus some c. Okay, this is good enough. Now, we have to find out the values of m and c, right? Let us randomly initialize step 1. Let's call this as step 1. Let's randomly initialize m and c. For example, here, let's randomly initialize m to be 0.5 and c to be, let's say, some 20. I just started it randomly. I have no clue whether these values are good or not. So any iterative process, learning here is an iterative process. So any iterative process will always start with some random initialization. And that's what we did here. We started with a random initialization. Now, how good these values are, we don't know, right? So let's substitute that. Or else, instead of 0.5, let me change this to, let's say, 10. So we will take m is equal to 10 and c is equal to 20. Okay. So now, if we substitute these values, 58 is equal to m is 10. So 10 into 5 plus 20, which will result in 50 plus 20, 70. So this is 58 minus 70. 58 is the original output. The output generated is 70. The difference between the original output and the output generated is, let's say, minus 12 in this case. Similarly, for second observation, 5.6 into 10, 56 plus c, 20, 76. So 64 minus 76. So this is like, again, minus 12. Third observation. What is our third observation? Okay, we will do it for last observation. 6 into 10, 60. 60 plus 20, 80. So 81 was the original value of the output. And what we generated is 80. So this is like 1. Now, for every observation, we are off by some number, right? Now, in the next iteration, let's say we keep m as it is. We will learn how to decrease or increase in a while. But just for the sake of it, let's say we decrease c to 10. Now, when we decrease c to 10, what happens? Because we did not change the m value, so 50 plus 10, so it becomes 60. So 58 minus 60, which is minus 2. So this is iteration number 1, and this is iteration number 2. In iteration number 2, so we have 58 minus 60, and for the second observation, 56 plus 10, which is like 66. So 64 minus 66 minus 2. And when it comes to the last observation, 60 plus 10, 70. So that is 81 minus 70, which is going to give us 11 plus 11. Okay. Fine. Which one is good? Obviously, by looking at these numbers, in iteration 2, we are much closer to the outputs than in iteration 1. But we cannot decide by looking at each and every value. It's difficult, right? So what we need is, we need a metric which tells us that which iteration is good. So what is that metric? Let's call this metric as RMSE. Root means squared error. Yesterday we discussed about, right? So these are nothing but your errors. Error for observation 1, error for observation 2, error for observation n. And similarly here, error for observation 1, error for observation 2, error for observation n. So we would square them up, sum them up. So square them up, we can call this as this. Mean of it, compute the mean of it. Then on top of it, we apply root. So that would give us RMSC. When we get least value for RMSC, that is the best relationship between input and output. Okay, so when we get the least value for this RMSC, what that means is when this line is very close to all the observations. Let me draw a second line, maybe that is coming from the second observation. So the second one is like this. Compared to red line, sorry, the black line, the red line was more nearer to the observations. So let's say for this one, the black line, we got a RMSC value of, let's say 100. And for this red line, we got a RMSC value of, let's say 60. Now, which is better? Obviously, the red line is better because it is having the least value for RMSC. So we need to find out, at what values of M and C we will get the least value for RMSC. That is the best value that explains the relationship between the input and output. But because this is very few observations, I am able to find out what is the best iteration by just looking at the data. But when we have too many observations and many input values and one output value, output will mostly be one all the time. Inputs can be any, inputs can be many variables. Output is always going to be one, right? So when we have many of them, this is very complex. So how do we represent the relationship between one input and many output? Let's say we represent that relationship as y is equal to beta naught plus beta 1 times x1, beta 2 times x2, so on, beta m times xm, where x1, x2, so on up to xm are inputs and y is the target. Now, this is how we can represent the relationship between many inputs with one output. Now, here, how many unknowns we have? This is the intercept beta naught. This is the coefficient, which is the slope for the variable x1. This is the coefficient for x2. This is the slope for x2. And this is the coefficient for xm, the slope for the variable xm. So now we need to find out what is the best value for beta naught, beta 1, beta 2, beta m, where let's say the RMSC takes minimum possible value, where RMSC takes minimum possible value. So how can we find out these values? That's a tough question, right? This is where we introduce the other concepts of mathematics. Let's say we can write this as, I am going to write this as y hat, y minus y hat. What is y minus y hat? Error. So y minus y hat whole square, that is error square. summation. Why we need to summation? If we have to take mean, we need to take summation. Summation for observation y is equal to 1 to n should be a minimum value. Then RMSE will automatically be a minimum value. So this here is called as the cost function. So in machine learning, whenever we want to learn something, we need to have a cost function. So this here is the cost function that we use for regression. So let's see how we can write this. Y minus beta naught plus beta 1 times x1 plus beta 2 times x2 plus so on beta m times xm whole square summation I is equal to 1 to n. So everywhere we would have I, and then we will have I here. Okay. Now this equation has to take minimum value. So how can we make sure that this equation can take minimum value? Let's do this. So this is a quadratic equation. Let's say this quadratic equation takes a shape like this. I am simplifying it with only two variables. So this is your beta naught and this is your beta 1. For different values of beta naught and beta 1, so let's assume that there is a third axis. So this is the third axis. This is your RMSE value. For different values of beta naught and beta 1, this is the value of RMSE. Let's say we randomly initialize beta naught is equal to something, beta 2 is equal to something. Let's say this is 10 and this is 20. We got RMSE value as some 120. Next, we need to find out the place where we get the minimum value for RMSE. Where we are getting the minimum value for RMSE, let's say this is 40. The minimum value that the RMSE can take is here. That is this, let's say beta naught dash, and this is this beta 1 dash. So we need to find out this beta naught dash and beta 1 dash. But when we initialized it with some random values, where this is your beta naught is equal to 10 and beta 1, let's say this is beta 1. So your beta 1 is equal to 20. Beta 1 is equal to 20. So this is where we are. Now we need to reach this particular step here, whether we have to increase the beta naught or whether we have to decrease the beta naught. That's a question. If we increase the beta naught, let's say we are moving in this direction. That means RMSE is increasing. When we decrease the beta naught, we are moving in the other direction. RMSE is decreasing. Which direction we want to move? We want to move towards the minimum direction. So we need to decrease the beta naught. So beta naught has to be decreased and beta 1 also has to be decreased. So if we decrease both beta naught and beta 1, we will move towards this minimum point. So how do we find this out? So for finding this out, we use an algorithm called as the gradient descent algorithm. So what this gradient descent algorithm says is, it will tell you which direction to move. So the gradient is nothing but the slope of the tangential line of this particular curve. So what is the slope of the tangential line for this curve at this particular point? So we can find that out using, so dou by dou beta naught for this equation, and let's call this equation as the cost function. So the dou by dou beta naught of cost function and dou by, these are partial derivatives of cost function with respect to beta naught and with respect to beta 1. So the sign of this gradient will tell you which direction to move. So using these gradients, we will update our weights. Now, beta naught is 10, beta 1 is 20. So this is iteration 1. Then beta naught 1, second iteration, beta naught beta 1 for first iteration, second iteration is equal to initial values of beta naught minus lambda times the gradient dou of cost function divided by dou beta naught. Similarly here, beta 1 minus lambda times dou of the cost function divided by dou beta naught. Now this lambda here is called as the learning rate. Okay. Now we would take iteration over iteration, iteration over iteration until we find this minimal point. The moment we find this minimal point, we will stop there. That is going to be the final values of beta naught and the final value of beta 1, where the cost function takes minimum value, right? This is exactly what we learned in our 11th standard. Maybe many of us didn't remember this. This is called as maximization minima. We popularly call it as maxima minima. To find out where a particular function can take its minimum value, we apply the first order derivative. Here, because we have two unknowns, we are applying the first order partial derivatives, which we call them as gradients. The gradients will tell you which direction to move. So using the gradient, we are decreasing or increasing the initial weights until we reach this point. The moment we reach this point, we will stop. How do we know we have reached this point? Any change to beta naught and beta 1 now will result in increase in RMS value. When it start to increase, no, we are moving in the wrong direction. So that's how we know we have reached the minimal point and we would stop there. And we have learned the weights beta naught and beta 1 from our training, from our learning. Now in future, if you want to find out the values of y hat, we could simply use this beta naught plus beta 1 times x1. So this is exactly what we call as learning. This is exactly what is happening inside this simple representation box, which we call as ML. Now, what did we choose here? We choose this function, a linear function, to represent this. Instead of choosing a linear function, if we have chosen a different function, then all these computations will change. So as a machine learning engineer, what we have to do is we need to choose the appropriate function that can represent the relationship between your input and output. Only then you would be able to learn and find out the unknowns in that function, so that we would eventually have a mathematical equation that can generate the output when we actually provide the input. Now in future, whenever you have an input value, you would be able to generate what would be the value of y. But the relationship between these two is learned through a machine learning process. And what happens in the machine learning process? This is what happens. First, we define the relationship between the input and then the output. We represent them in a general equation form, like y is equal to mx plus c, or y is equal to beta naught plus beta 1 times x1. Now we need to find out those values of unknowns, beta naught and beta 1, which represents this best line in such a way that we have the best relationship between our input and output. For that, we would always need a cast function. So in this case, let's say we are using the cast function as RMSC. So we need to find out the minimum value of RMSC where for a given value of beta naught and beta 1. That's the objective. So we are creating a cast function. So this is our cast function. We randomly initialized our weights. So here I took only two unknowns because in a multi-dimensional plane it would be difficult to represent. So beta naught and beta 1. So if with your cast function for this would look like this, yi minus beta naught plus beta 1 times x1. So this is going to be our cast function. Sigma I is equal to 1 to n. So we need to find out the values of beta naught and beta 1 where this entire cast function takes the minimum possible value. Since this is a quadratic equation, this equation might take this shape. I represented this shape with this curve. When we randomly initialized the values of beta naught and beta 1, so we found out what is the value of this curve, where it falls on this curve. But we want to reach this minimum point. So to reach this minimum point, we are using the concepts of calculus, finding out the gradient of this curve, which will tell us which direction is the minimum point, and we would gradually take those steps so that we reach this minimum point. How do we know we reach this minimum point? Whenever we change the values of beta naught and beta 1 further, we would overshoot, and then the value of RMSC will start to increase again. So that is an indication that we are crossing the minimum point and we stop at the minimum point. And those values of beta naught and beta 1 are going to be the final values that represents this equation. And this is what we have learned through a machine learning process. So far, so good. Okay, let me take a pause here. Let's see if there are any questions around this. Yeah, fine. If you are hesitating to ask, please hold on. Again, at the end of the session, we will have 15 minutes dedicated only to have the Q&A. The reason I am explaining this process, I know this is a slightly complex process. It involves a lot of mathematics over there. And for a beginner who is listening to this for the first time, it's easy to get overwhelmed by the amount of concepts that is hidden behind that machine learning layer. But don't worry about it. All these concepts that I'm explaining is to show you the depth of machine learning, how far machine learning goes to learn something from the input and the output that we are actually giving. Implementation will not be this complex at all. In Python, we would probably write hardly 10 lines of code to do all of this, and everything happens behind the scenes. You don't even realize so much amount of calculations are happening behind the scenes, and finally you get an output. I'll show an example. Then you would say, wow, machine learning is so easy. Yeah, it is made easy with the help of the programming languages like Python and R. But if we have to understand the raw concept behind this machine learning and AI, that's when things become very, very complex. But having a good understanding of what happens in the machine learning behind the scenes is very essential to be successful in this world. When you see a AI example, maybe tomorrow we would see an AI example where I'll introduce you to a new concept called as neural network. Today, when people say AI, it is all about neural network. Gone are those days where we try to learn using heuristics, we try to learn using some mathematical analogs, etc. Not anymore. When we talk about AI in the real world today, it is all based on learning, and that learning is coming from one of the most sophisticated um, uh, algorithms, or I would not call it as an algorithm, but one of the sophisticated blocks of machine learning, which we call as the neural networks, the neurons, right? When I introduce them tomorrow, you would have to recollect all of these things. If you have no clue about what is happening inside a machine learning, you would never be able to learn what happens inside that neuron. So to make that to make it easy to understand what happens inside a neuron, I'm first of all introducing you to the concept of machine learning. Okay. So this is only one side of the coin when we are trying to perform a regression. Now let's look at another example when we are trying to perform a classification. So how does classification looks like? So let's say we have X, which is our input, and Y, which is our output. X, let's say X takes values like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And these are our input values for X, and Y take values like, because classifier should always be discrete, like zeros, ones, or A, B, C, but it has to be discrete. It is not numbers, right? So let's say this is 1, this is 0, this is 0, this is 0, this is 1, this is 0, this is 1, 1, 1. So this is the input and this is the output. Now we have to generate a rule or whatever it is that can create this output from this input. Now, classifier problems are very different. If we compare this with the regression problem, where you have X and Y, which has values like this, and we try to represent that with a line, the same cannot be done for classifier. So that's why it is altogether a different problem to handle. So given this data, let's say I go by a simple rule. The rule is like this. If X is less than or equal to 5, then Y is equal to 0. Else, that means when X is greater than 5, then Y is equal to 1. So this is just like a if-else rule. So this is called as the divide and conquer. This is the basic foundation for decision tree based algorithms, right? To start with, our output, I am talking about my output. My output takes two values. The values are 0 and 1. Okay, so this is our output. And how many observations are there for 0? 1, 2, 3, 4, 5. So for 0, I have 5 observations. And how many for 1? 1, 2, 3, 4, 5 again. So we have 5 observations for 1. So this is our output. Now we need to separate these observations, separate the observations that belong to 1 and separate the observations that belong to 0. That means we have to know when Y will take a value of 1, when Y will take a value of 0. Now, the divide and partition generally happens like this. Division happens on input variables. What input variable we have here? X, only X. So X less than or equal to 5, S this side, no this side. So these observations will go to the left child. So this is called as the parent node. And this is the child on the left hand side. This is the child on the right hand side. So on the left hand side, we got 5 observations. On the right hand side, we got 5 observations. On the left hand side, among the 5 observations, for 0, we got 4 observations, and for 1, we got only 1 observation. On the right hand side, for 0, we got 1 observation. For 1, we got, let's say, 4 observations, right? Now, with this rule, if you can observe here, majority of them on this left hand child belongs to 0 category. So I can say that, hey, when this rule is satisfied, y is equal to 0. On the other hand, where majority of them belongs to 4, so when this rule is not satisfied, then y would take a value of 1. So this is a simple way of separation. And how do we generate this rule? That is where it becomes very tricky. Why it becomes very tricky? See here, I can generate a rule like this: x less than or equal to 1, x less than or equal to 2, x less than or equal to 3, so on all the way x less than or equal to 9. So I can take any of these rules. Now, which rule is giving better separation between these classes? That means, which rule is giving majority of the observations in that belong to the same class in one node? So that is this rule: x less than or equal to 5 is the one that is giving majority of the observations that belong to the same class fall in one node. On this side, I got observations that belongs to 0 class, and on this side, I got observations that belongs to 1 class. But out of all of these rules, we can say x is like x less than 5 is x less than or equal to 5 is the best rule. But how do we quantify it? So we cannot use manual verification like this. So we need a metric, just like how we have a cost function in case of linear the regression example. Here also we need a metric that says which is giving us a better separation. So that metrics are called as measures of impurity. So what are the measures of impurity here? The generally used measures of impurity are entropy and Gini. It's called Gini index. So these are the two measures which are used to decide whether the separation, whether the split that we have made using X is really separating your Y well or not. So what is this entropy? So entropy is measured as negative times sigma pi log pi to the base 2. I is equal to 1 to k, where k is the number of classes. Then what is Gini? 1 minus sigma times pi square. So this is Gini index. I'll show you a simple example to represent how Gini and entropy works. Let's say we have a node like this. So this is 5 observations that belong to no class and 5 observations that belong to S class. What is the Gini and entropy of this node? Let's first compute entropy of this node. So entropy is equal to, how many classes we have? 2. So that is minus 5 by 10, where pi is the probability of the ith class. So probability for the no class and probability for the S class. So that is why minus 5 by 10 log of 5 by 10 to the base 2. So this is for no class. We are completing no class. So similarly, we have to do it for S class. So sigma I is equal to 1 to k. So that's why again minus 5 by 10 log of 5 by 10 to the base 2. So that is for the S class. So what happens here? Minus 1 by 2 log 1 by 2. So I would write this as log 2, 2 to the power of minus 1. Again here minus 1 by 2 log 2 to the power of minus 1 to the base 2. Minus 1 comes here. So this is 1 by 2. Log 2 to the base 2 is 1. Again minus comes here. So log 2 to the base 2 is 1. So 1. Entropy for this node is 1. So we calculated the entropy for the parent node. So for the parent node, entropy is 1. And let's calculate Gini. Now Gini is equal to 1 minus, for the first, what is the probability of the ith class? 1 by 2 whole square. Then what is the probability for the second class? So that is also 1 by 2 whole square. So that is like 1 minus 1 by 4 plus 1 by 4, which is 1 minus 1 by 2.5. For the parent node, Gini is 0.5. This node here is perfectly impure node. For a perfectly impure node, when do we call it as a perfectly impure node? When the observations are same for both the classes. It's like 50% water and 50% dust particles. That's perfectly impure water, right? So here 50% of them belong to no class, 50% of them belong to S class. So that's why this node is a perfectly impure node. So for a perfectly impure node, entropy is 1 and Gini is 0.5. Yeah, someone is having a question. Please feel free to ask or post it on the chat window. I know this is a lot of stuff, difficult to understand, but please ask or post the question. Okay. Meanwhile, I'll explain the remaining concept. You post the question. I'll answer that for you. Thank you. Okay. For a perfectly pure node, let's see for a perfectly pure node. So what is a perfectly pure node? When all the observations belong to one class and no observation belong to the other class. So this is a perfectly pure node. So let's see what is the entropy value for a perfectly pure node and Gini for a perfectly pure node. So the entropy here is minus 10 by 10 log of 10 by 10 to the base 2. And the other one is minus 0 by 10. So I don't need to even write it. So this is log 10 to the base 10 is 1. Log 1 to the any base is 0. So entropy is 0. So for a perfectly pure node, entropy would be 0. And similarly, let's see Gini. Gini is 1 minus 10 by 10 whole square plus 0 by 10 whole square. So this is 1 minus 1, 0. So Gini is also 0. So the purity of a node is decided by the value of entropy or Gini. If entropy is 0, that means the node is a pure node. All the observations belong to the same class in that node. When entropy is 1, the node is an impure node. All the observation belongs to equal number of observations belong to both the classes. So that's how we define a perfectly pure node and perfectly impure node. For a node which is anywhere in between these two, let's say now one of the child node we have, no has 4 observations, S has 1 observation. So what would be the entropy of this? Minus 4 by 5 log of 4 by 5 to the base 2 minus 1 by 5 log of 1 by 5 to the base 2. So this would roughly around be 0.2 if we compute this. And what would be Gini? Gini is 1 minus 4 by 5 whole square plus 1 by 5 whole square. So this would be something like 0.18 or whatever it is, right? So for a node in which majority of them belongs to one class, you would see entropy value closer to 0 and Gini value closer to 0. For a node where you see equal number of observations for both the classes, in this example here, in where you have both 5 and 5, entropy is 1, Gini is 0.5. Now, whenever we are generating a rule, we need to generate a rule that gives maximum separation between the entropy at the parent node or the root node versus entropy at the child node. So entropy at the parent node here is 1. Let's say entropy at the child nodes, left hand side child is 0.2, entropy at the left hand child ECL is 0.2, entropy at the right hand side child ECR is equal to 0.2. Now what is the entropy for this entire split? We do a weighted average of these two. 0.2 into how many observations are there in the left hand child? 5 divided by 10 plus 0.2 right hand side into how many observations are there in the right hand side? Again 5 divided by 10, which is going to be 0.2. The decrease in entropy is called as information gain. So information gain is entropy at parent node E0 minus entropy at child node E1. In this case, 1 minus 0.2, 0.8. Whichever rule gives the maximum decrease in entropy or the maximum decrease in Gini, that is the best rule. That's how we try to learn how to separate a discrete variable using the input variables. Okay, yeah. Now I'm open for question. Okay, you want me to explain the entropy again? I will do it, not a problem. So entropy is called a measure of impurity. Impurity is measured at node level. Given a node, how impure or how pure that node is. When you have a node which has equal number of observations for both the classes, it is called as impure node. When you have a node which has observations, all of them belong to the same class, that is called as a pure node. But we need a metric to measure the level of impurity, and those metrics are called as entropy and Gini. Now, how does we measure this entropy? The formula for entropy is given like this. Entropy E is equal to minus sigma I is equal to 1 to k, where k is the number of classes, probability of ith class into log of the probability of ith class to the base 2. That's how we compute this entropy. Okay. So here for this example, we have computed the entropy minus what is the probability for the first class? 5 divided by 10, because total number of observations in the node is 10 and 5 observations belong to this first class. So that's why probability for the first class is 5 by 10 log of 5 by 10 to the base 2. And for the second class, For the second class, how many observations belong to the second class? Again 5. So probability of second class is 5 by 10, log of 5 by 10 to the base 2. So this is how the rules are generated. Here we are learning through a tree-based approach. This approach is called as decision tree-based approach. If we try to take a different approach, then the whole concept of learning will change. If we choose a different algorithm, then the whole concept of that algorithm would be very different. But I wanted to give you an example of what learning means when we are using a classification problem. So here our target is discrete, our output is discrete. So we are going with a classification problem and using a tree-based approach, using a decision tree-based approach, how can we learn? And that's the goal. We are trying to learn how to separate the classes, how to separate the classes with the help of generating the rules. So this approach is called as recursive partitioning. We are trying to divide the data into smaller things so that we would ultimately, at the end of the day, we separate all of them. Now, let's see, we have more variables, x1, x2, x3, so on up to some xk, and then the target variable y. Target variable y is binary. Now, how this happens is, again, we start with the root node. So this is our root node. We would make the first level split. Let's say this is x1 less than p. So this is the first level split. Whichever variable gives the maximum decrease from E0 to E1, that variable will make this root node split. So we have to compute the entropy of root node. We have to compute the entropies of all possible splits in x1, x2, x3, all the way up to xk. Whichever variable, I'm assuming x1 is the variable that is giving you the maximum decrease here. So that's why this variable is making the root node split. If x3 is decreasing this maximum, decreasing the maximum entropy, then x3 will make the root level split. Once this is done, this become a parent node, this become a parent node again. We can continue to split this further until we separate all the classes. Our objective is this becomes leaf nodes, this becomes the root node, and these are our intermediate nodes. So we continue this process until we separate the observations and form the leaf nodes. Once we have these leaf nodes, this tree is the rule-based tree that we have learned from our input data. Now using these rules, like if x1 less than p, then this side. Then nested condition. If x3, let's say this is x3 less than some k. If x3 less than k, then this side. So it will reach this node. Whatever is the maximum number of observations, which class is the dominant class in this leaf node, that is going to be our y value. Then y is equal to, let's say, 1. In this case, all of them belong to 1. So this node belongs to 1. In this node, all of them belongs to 0. So this node belongs to 0. In this node, majority of them belongs to 0. So this is 0. In this node, majority of them belongs to 1. So this is 1. Now, when we pass a observation to the tree, which leaf node it ends into, that is going to be our prediction. But how did we came up with this? How did we learn how to find out the value of y? Using the input variables, using a tree-based algorithm, which is called as the decision tree. Okay, so far so good. Yeah. Another person was asking a question related to statistics. Not a problem. I'll try to answer my best. Please post your question that is related to statistics. Okay, so this process is exactly what we call as learning. And this process will vary depending upon our problem statement. Like I gave a couple of examples, right? One regression example, another classification example. In the regression example, we used altogether a different mathematical approach to explain, to generate the output from the input. That is using the linear algebra, the linear equation, that is y is equal to mx plus c. When our problem statement is altogether different, we have to use a different approach. So in this case, I opted for a decision tree based learning. Why? My objective is to separate the classes from each other. At the training process, at the root node, I have all observations clubbed. Observations that belong to no class and observations that belong to S class. My motivation is to learn rules that can separate the observations that belong to no class and the observation that belongs to S class. So here, our ultimate goal is to reach those leaf nodes where majority of those observations belong to the same class, or all the observations belong to the same class. So this tree learning process will continue as long as we are able to decrease the entropy, or we are able to decrease the Gini from the parent node to the root node. And this trees doesn't have to be symmetric. Like I have drawn a symmetric tree here, it doesn't mean that it has to be symmetric. So if this root node is split using x1 and we got a left hand child and a right hand child, let's say right hand child, when we try to split the right hand child further with any of the other variables that we have, we are not able to decrease this entropy any further. So then it stops here. This becomes our leaf node. But on the left hand side, this node, we are able to split further using the variables until we reach to a point where we would not be able to decrease the entropy. We are not be able to decrease the Gini further, and it stops there. That's when our leaf nodes form. So this process is what we call as the learning process. Okay. Any more questions that I can help you with? Okay. Then we need to also see how good this model is. Similarly here, to see how good our learning is, we need to have a test data. And on the test data, we would test data is, like I said yesterday, when we have our input data like this, where you have x1, x2, so on up to xm and y. This is our target variable, and we divide this into two portions, 80% of them into training and 20% of them into testing, right? Then in the training process, that means when we are trying to learn this decision tree, we only use this training portion. So that's why this is fed to the decision tree algorithm. And the decision tree algorithm tries to learn and generate a tree for us. Now, with the help of this tree, we can make future decisions. Now, we pass this test data to the tree, which we have learned, and the tree will give us decisions, which we also call as predictions. Now, on this test data, you have y, which is the actuals, and we also have the decisions given by the tree. We call as them as y hat. Now, we need to find out how good our learning is, how good our tree is in making the decisions, right? So for that, we use metrics like, let's say, accuracy, and we can also use metrics like error. So what is accuracy? Number of correct decisions that we have made divided by total number of decisions. So for example, if you have y and y hat like this, 0, 0, 1, 1, 0, 1, 1, 0. These two are correct decisions when y and y hat, when the original value is same and the decision is given by the tree is also same. These two are correct decisions, but these two here are wrong decisions. So our accuracy here is 2 divided by 4. Total decisions made is 4. Out of them, 2 are right. So our accuracy is 0.5. Error is wrong decisions divided by total decisions, which is like again 2 by 4 in this case, 0.5. So these metrics like accuracy and error tells us that, hey, how good your learning process is. If you make decisions using this, how good your decisions are going to be. That's going to be judged using these two metrics. Fine. This is all about machine learning. Of course, there are tons of algorithms. I have only covered two here, one for the regression example, other one for the classification example. But if we have to learn machine learning as a whole, we have to definitely learn a lot of different algorithms, because the way these algorithms learn will differ from one algorithm to another algorithm. But my intention is to exhaustively give you an overview of what happens when someone says, hey, this is machine learning. This is happening behind the scenes. But machine learning has limitations. It has limitations. Why? Especially, it assumes that there is a relationship between your input and output, and your entire learning process is purely based on that assumption. For example, in this case, the assumption here is the relationship between input and output is a linear line, and it is trying to represent that in the form of a linear line. What if your data points are like this instead of a linear line? So your data points are like this. Now, instead of a linear line, maybe something like this will be a better fit, better representation of your input and output. But your machine learning, the reason you are representing this with the form of a linear equation, will never learn like this. It would always try to learn a linear line like this. So for very complex problems, these simple representations of linear lines is not going to be a perfect explanation of the relationship between input and output. So we need a lot of non-linear functions, a combination of a lot of non-linear functions to represent this. So that is the complexity where machine learning faces a lot of challenges. And here also, what if there is no separation like this exists at all in the first place? Like, how did we separate x1 less than or equal to 5? And we did we computed the entropy, and we computed the entropy at root node and the child nodes, but none of these input variables were able to give that separation, because the relationships between x and y is so complex that a linear boundaries like this is not able to separate the classes very well. In such cases, we need a much more complex, we need a much more rigorous learning methods than all these algorithms that we have seen so far. Okay, so what are they? How do they learn? What is the difference between these learning, which is based on some mathematical functions, versus the other type of the learning, which is much more complex in nature, that we would see tomorrow. For now, let me show you a quick example of, okay, there is so many things that is happening inside this training. So if you see this example, there is a lot of calculations happening. For one variable itself, I had to do so many calculations. Imagine if I have 10 input variables and one target variable, how many calculations has to happen in generating this? It's practically impossible to do these type of learnings with manual process, right? So that is where these programming languages like Python and R comes to our rescue. So I'll just give a quick walkthrough of how we can build a tree-based algorithm so fast and so easy with the help of Python. So see here, by the way, if you are not familiar with Python before, if you have no clue how Python works, this would be a tough challenge for you. Please excuse me there. I'm assuming that at least you know some concepts of Python. If you are interested in AI, I strongly recommend you to start learning Python right away. That's going to be your bread and butter if you are interested in any sort of doing machine learning or AI. Even if you are not interested in AI, Python is still a beautiful programming language for application development, software development. But in AI world, Python is our bread and butter tool. So that's why I'm coaching so much for Python. So just like how in C++, you have like include math.h, include stdio.h, something similar here. We call them as modules. So this is a module, sklearn, scikit-learn is a module. In this module, we have a submodule called tree. In this submodule tree, I have a predefined function called as decision tree classifier. So I want to use this decision tree classifier function to build my decision tree. So it's like hash include stdio.h. So that's the same statement that we are making. From sklearn.tree, import decision tree classifier. Of course, a whole bunch of other things there, but you can ignore them. This is my data. So I have a file here. I can fetch this file from a database. I can query this file from a data table on a database anywhere, but I have this file in my local drive itself. So I'm trying to read this file into Python. And whenever we read such files, it creates a table-like structure. And we call that table-like structure as a Pandas data frame. So for data analysis in Python, Pandas is the most heavily used module. So you need to know what Pandas is and how Pandas work. So we have created a table, which we call as a data frame, Pandas data frame here. And you can look at this. I have printed few records for you. So these are all the observations that we have. And these are all the variables that you have, the variable names that you can see. Let me show you chrn.shape so that this table now has 3,333 observations and 21 variables, 21 columns. Out of this column here with the name churn is my target variable. This is my output variable. So in terms of business, this means that the customer is going to leave the business. So the decision here, what decision that we are trying to make here, we are trying to find out who are the customers who will leave this business. So if a customer leaves the business, then this value will be 1. If the customer is not leaving the business, then this value would be 0. So what type of decision making that we are trying to learn here is what makes a customer to leave the business. Now, if we know that, if we have that knowledge, we can avoid customers leaving us in future. If this is what is making a customer to leave us, we can take action to avoid that. That's how all of these machine learning, all of these data science is going to help the business, right? Knowing, gathering the knowledge from your data and using that knowledge for your future decision making. Now, let me quickly show you how I can do this. I'm not going to use these input variables because they are useless for a reason. So I'm dropping them off. So my target is this variable churn. Except this, rest all of them are going to be my input variables. So I have separated my target variable and I have separated my input variables. Here we are creating a split between the training portion and the test portion. Test portion will have 20%, training portion will have 80% of the data, and this is going to be done randomly. How this works, that's why you have to learn Python, right? Fine. So we have created a training portion and the test portion. So decision tree classifier, this is the algorithm that I am going to run through the data to learn the tree. And once I run this, I will learn the tree, which would make my decisions in future. So let's run this. So my initialization is done. To this, I have to pass the data. So this initialization, this is an alias we are giving to this decision tree classifier. Alias.fit is called the training process here. My input variables are in x_train and my target variable is in y_train. And the moment we run this cell here, it learns a model and the model is ready. And if I want to visualize this is how I can some problem there. Previously it had that tree based visualization. I think now I've overridden one of these modules. I have to roll it back so that it would work again, but that's just for the visualization. Nothing to worry about my model. My model is ready. Now I have the test data set, which I have not used during my training process. So in this step, I have created my train and test. I have only used my training portion. I did not use my test portion. On the test portion, this is the tree that we have learned, and using this tree, predict on the test data set. Let's see how good you are going to predict. And we get something as an output, which is the predictions. Now, how good these predictions are, so we try to generate that with the help of the confusion matrix. Don't worry about this. Our accuracy here, these two are our correct decisions. So what is our correct decisions? Accuracy score of y_test, comma, prediction. So we have all inbuilt functions. We are 92% accurate in making our decisions.
Need to disturb you.
Sorry, sir. Go ahead.
Is there any chance that the size of that text can be increased? Because in the YouTube it is coming as blur.
Oh, sure, sir. We can increase.
Okay. Thank you. And some questions are posted in the chat box, sir. Maybe after this session.
I will. Oops.
Yes,
Oops.
thank you.
Is that okay now? Now the font is fine?
1 minute, sir. A little bit more, sir, maybe, if possible.
Yeah. It gets distracted a little bit.
Okay, sir.
Okay. Now they should be able to see.
Yes, sir.
Okay. Yeah. So without much effort, it hardly took me 10 minutes to write this code. Without much effort, I am able to make predictions with 92% accuracy. That's the beauty of it. Of course, this is a toy example. This is not a real example. But even when we go to the real example, we would have to spend a little more time on how we we set this problem up. But coming to the code part, it is hardly these 14 lines of code that you see here, nothing more than that. That's the simplicity when we use these programming languages like Python and R. Okay, you don't see any of those computation complexities. Like when you try to learn what is the concept behind this machine learning, you have to learn all of these things: entropy, Gini, information gain, and what is impurity, how we are trying to do the splitting. But the moment when you try to perform an application, like when you try to learn something from a historical data and build a machine learning model by yourself, it doesn't look that complex. It is like hardly 10 lines of code, and I'm able to show you a accurate predictions with an accuracy of around 92%. So that's the beauty of this machine learning. It works well with some data sets, but it doesn't mean that it would work well with every data set. Depending upon the complexity of the relationship between your input variables and then the target variable, we have to choose different types of algorithms. So that is where the experience of a data scientist would come into the picture. The experience of a machine learning engineer would come into the picture, right? So all of this is just the ML side of it. In the first 2 days, we did not touch anything about the AI side of the world. I want to set these basics so that I would be able to easily explain the AI side of the world, which we would be doing tomorrow. We would start with what a neural network is, how a neural network will try to learn, what is the difference between a machine learning based algorithm versus that neural network based algorithm. Then you would understand why AI is so complex, why AI is so popular these days. Okay. Let me look at the questions. Unsupervised learning example. Yeah, I can give, but again, it would get deviated. But let me hold on. If we have time on the last day, I would certainly give you a unsupervised learning example as well. Hyperplane can be nonlinear also. Yes. For example, if you imagine a blanket just floating in air, it would not maintain that flat shape, right? It would maintain ups and downs. So that's also a hyperplane, but not like a non-linear hyperplane. And we can learn non-linear hyperplanes using neural networks or using some other complex algorithms. Yes. But here, for simple example, we have used a linear hyperplane. Okay. Regression and classification, no need to combine them. The objective. So when do we go for regression and when do we go for classification is based on the objective. So if your objective is to predict the resale price of a car, then it is a regression problem for you, and classification doesn't help there. When you are trying to predict the likeliness of a disease like cancer in patients in the medical world, this is a classification problem. Regression would not help there. So these two are different worlds altogether. When we choose our problem statement will decide whether we have to perform a regression or whether we have to perform a classification. Okay. There are algorithms which can perform both. There are some algorithms which can perform both regression, or it can also perform classification. But the objective that we are trying to solve will decide whether we have to go with a regression problem or whether we have to go with a classification problem. Not mandatory to take training 80 and 20 all the time. It can be changed. Generally we go with 80-20, depending upon the size of your training examples, the number of observations in your training set. You can increase your test set or you can decrease your test set. Huh. Uh, to start with, how to choose M and C values randomly. So these are initialized by the algorithm. So we have something like np.randomn, which uses a normal distribution to initialize the values. And initializing the values of M and C itself is a huge concept by itself. So depending upon the type of the data, we can choose different types of initialization. But using a random normal distribution is the common initialization. So you can think of how right now as we choose a value, arbitrary value of m and c based on the average values of your y as of now, so that it would keep your thinking simple. The more you deep dive into this, the complexity would be like going. You can reach that stage maybe a little later. For now, let's keep that simple. It is randomly initializing for you. How it does, let it be there. We would learn about it little later. I can send these Jupyter notebooks. I can send these files. I'll do one thing. I'll put these data file and as well as the Jupyter notebook into a GitHub and share the GitHub link, so you can copy everything from that GitHub. And I'll ask Kiran sir to circulate that GitHub link so you can pick it from there.
Sure, sir. Thank you.
Okay. Any other questions on YouTube that I can help?
Maybe no more questions, sir. If you have any
Okay.
doubts, you please post in the YouTube chat box or in the Zoom chat box. If you have any more questions, please post them.
Tomorrow's class is going to be even more interesting because we are going to break the ice called the neural network. If you understand that, that is going to be the foundational block of your AI. If you understand that very well, believe me, you can learn a lot of AI by yourself. The difficulty that a lot of people face when they start their journey of AI is the moment they look into how a neural network works, they get scared by the amount of math and the amount of computation complexity behind the scenes. But if you just pass that stage, if you break that ice, then rest of the AI is going to be pretty smooth and pretty interesting for all of you. So be more attentive tomorrow so that you understand that basic building block of the entire AI, which we call as the neural network. And I'll show you an example of how to program a neural network also in our last day session. But maybe for the next 2 days, we would spend our time heavily on decoding what exactly a neuron means, what exactly a neural network means. For some of you who are not familiar with any of these concepts before, I can understand this could be a lot of information for you, and it would be overwhelming for people who are looking at it for the very first time. But the more the amount of time that you spend on this, it becomes easier for you. Don't get bogged down by looking at all those computations. And that's the reason I showed this example. 10 lines of code and your model is done, just like a magic happens. Then what else you can expect? So that's the level of simplicity that is brought in by these programming languages and the modules available there. So don't think heavily because of that math that I have shown you. That math and all is to make you realize the potential of what machine learning is, potential of what AI can do to the world in future. But that is taken care by the programming languages. You don't manually calculate anything. No, AI is not robotics. To train a robot, they use AI, but AI is all over the place, right from the camera in your smartphone to all the way up to robotics. AI is playing a significant role behind the scenes. Okay, imagine you are taking a picture with your smartphone, and you take a picture, and in place of that smartphone I will give you a digital camera, and I ask you to take the same photograph with the digital camera, and look at the difference between the picture that is taken by your smartphone versus the picture that you took using a digital camera. And that difference is what AI brings into. Anybody can take fantastic pictures using smartphones because the AI behind the scenes is playing a lot of optimization for you to get the best picture out. But when a digital camera is given to you, you have to set the right settings on the digital camera to click a similar picture, like adjusting the exposure, adjusting the focal length, everything, ISO. That's not possible for someone who is not used to a digital camera. But everybody is a fantastic photographer when they have a smartphone in place, right? So that's AI for you. That's AI helping you to get a best picture there. This is a misconception that people, when they hear this term AI, they imagine that a robot speaking, a robot doing stuff. No, that is also AI. I'm not discarding that, but having that misconception that AI is all about robots is not true. AI is all over the place, right from medical imaging, medical diagnosis, to your smartphones, the chatbots, the Amazon Alexas, and then Google Homes, your Google Assistant. Everything is powered by AI behind the scenes. Okay, that's all I have today. I hope this session was useful. Tomorrow we will be looking at more interesting things. See you all tomorrow.
Sir, thank you, sir. All the participants' feedback is already posted in the chat box for day 2, as well as in the YouTube also it is posted in the chat box. If anyone has not given, please give the feedback before leaving.
No questions on YouTube, sir?
No, sir.
Okay.
Already I posted all.
Okay, sir. Thank you.
Yeah. Okay, sir. Maybe we can.
Okay, sir. Fine. Yeah, I'm leaving the session. Thank you.
Thank you, sir. We'll meet again tomorrow.